Right, so this video is going to be about centre of mass and collisions, and we're going to expand our ideas out to two-dimensional collisions. So we've already touched on the idea that momentum is conserved as long as there are no external forces acting, as long as it's an elastic collision. That means that the velocity of the centre of mass is going to be conserved too. Because of the work we did last week, we can understand that the centre of mass and the movement, or lack of movement, of the centre of mass will be conserved during a collision. And that's true both in one and two dimensions. So we're going to scale it up by looking at two-dimensional situations. So that means we can do some vector work with the velocity of the centre of mass. Now, I don't want you to panic about what the vector work looks like, okay? Because you're already really familiar with the idea of vectors and the idea that vectors come with more than one component. So we're going to be looking at both the x and y components. And here's a really simple example. So if we have two identical objects moving on a friction-free surface, so say they're parked on ice or on an air hover table, and they're moving with the same speed at right angles to one another. Now, I think you can agree that as long as these two have the same mass, that the centre of mass must be located between them. And we're going to mark that on here. There's our centre of mass. And I think you'll be able to agree that if this puck is moving at 1 metre per second, then the centre of mass must travel in a y direction by 1 metre every second. And you'll also agree that if this one is moving at 1 metre per second this direction, then the centre of mass must also move 1 metre per second in that direction. And the net result is that the centre of mass has a certain overall velocity. Okay, and we can work that out using vectors. We can make a vector triangle 1 metre per second that way, 1 metre per second that way, and look for the hypotenuse. If we move to a second later in time, we can see that this object has dropped and this object has moved across, and they're in their new positions. But they're still separated, and the centre of mass is still between them. And we can still, I hope, agree that if it's moving at 1 metre per second, this will also be moving, if this is moving, and so the centre of mass will continue moving with a steady velocity. Now, if we look from that diagram to this one, and it's a shame we can't draw them one over top of the other, but you'll see, my terrible drawing notwithstanding, that the centre of mass is moving at a steady and even speed, independent or dependent on, but can be conceptualised independently of the movement of these individual components. If we understand how they move, we can say how the centre of mass moves, even if the centre of mass is not a real part of the object system. There's just empty space between them. So I hope that's clarified some of your understanding. We're going to move on to looking at conservation of momentum in a little more detail.